Welcome back to Part 2 of Section 9.2. Remember in Part 1, we talked about how to find a point estimate, and we talked about students' t distribution, and I showed you how to read the t-table. Now we are finally ready for the main event, which is to learn how to construct a confidence interval for a population mean on our own. Now, before I give you this formula and you just start plugging stuff into it, it's very important that we understand the conditions under which this formula is valid. The reason statistics can have such a bad reputation sometimes is because people use formulas in places where they don't apply. So we need to understand what kind of conditions are necessary before this formula is valid. For one thing, the sample data that we use must come from a simple random sample or a randomized experiment. Also, the sample size must be small relative to the population size. In other words, the sample needs to be less than 5% of the overall population. And third, the data need to come from a population that is normally distributed, or if we don't know that the population is normally distributed, then the sample size must be large. That is, sample size must be greater than or equal to 30. So a 1 minus alpha percent confidence interval for mu is given by the formula x bar minus e and x bar plus e, where e is calculated by t sub alpha over 2 times s over the square root of n. Now remember, t sub alpha over 2 will come from the t-table with n minus 1 degrees of freedom. Remember, s is the sample standard deviation, and n is the sample size. Now notice that alpha is the area in the tails of the distribution. So alpha over 2 just means the area in one tail. Because this confidence interval uses the t distribution, it's often referred to as a t-interval. Now, as we've said before, for sample sizes of 30 or more, the central limit theorem guarantees that the sampling distribution of the sample mean will be normal. But for smaller samples, if our sample contains outliers, that's a problem. Remember, the sample mean and the sample standard deviation are not resistant. Therefore, if the sample contains outliers, the mean and standard deviation will not do a good job of representing the population, and our t-interval will not be valid. Therefore, if you don't know for sure that the population is normally distributed and you have to work with a small sample, then before you use this method, use a box plot to determine that there are no outliers in your sample. Also, we should look at a normal probability plot like the ones we talked about in section 7.3 to determine if the sample looks like it came from a normal distribution. Now remember, if the problem tells you that the population is normally distributed, then you won't need to look at the normal probability plot. And if the sample size is 30 or more, then you won't need to look at the normal probability plot or a box plot. So finally, here's our first example where we'll get to construct our own confidence interval. The problem says, how much time do Americans spend eating or drinking? Suppose for a random sample of 1,001 Americans aged 15 or older, the mean amount of time spent eating or drinking per day is 1.22 hours with a standard deviation of 0.65 hour. A histogram of time spent eating and drinking each day is skewed right. Use this result to explain why a large sample size is needed to construct a confidence interval for the mean. Okay, remember, whenever the original population is not normally distributed, the central limit theorem guarantees us that the sampling distribution of the sample mean is normal only if sample size is 30 or more. So we could say that since the underlying population is not normally distributed, we can only be sure that x bar is normally distributed if n is greater than or equal to 30. And part B, determine and interpret a 90% confidence interval for the mean amount of time Americans aged 15 or older spend eating and drinking each day. Okay, we know from the problem that the confidence level is 90% or 0.90. Therefore, we know that the area in the tails is the complement of that, so we know that alpha equals 0.10. Remember, alpha stands for area in the tails. Now, sometimes a diagram helps us figure out what t-score we need, so if it's helpful to you, draw yourself a diagram where the confidence level is the area between the two t-scores we're looking for. Now, if area is 0.1, we know that the area in each individual tail will be 0.1 divided by 2. So the area in each tail is 0.05. Now we know that n is 1001, and therefore we know that degrees of freedom is 1000. And using an area of 0.05 and a degrees of freedom of 1000, you can go to the t-table and find out that t sub 0.05 is 1.646. Now remember that the x-bar given in the problem was 1.22, and now we need to calculate our margin of error. So E equals t sub alpha over 2 times s over square root of n. T sub alpha over 2 is 1.646, s is 0.65, and square root of n will be square root of 1001. Now I do not want you to get a decimal approximation for this, because if you get a decimal approximation here and you round off, and then you do your adding and subtracting and round off again, that could cause problems. So I would just leave this in exact form just like it is. Now the lower bound of our confidence interval is going to be x bar minus e. So in your calculator you'll just enter 1.22 minus all of this, and you should get 1.186. And then for the upper bound, you'll enter x bar plus all of this, and that's going to be 1.254. Now I know you don't want to have to enter all of this twice, but like I also said, it's not best to convert this to decimal form and then have a rounded off value. So in just a minute, I'm going to show you how you can recall commands on the calculator and change your minus to a plus so you're not entering everything twice. So it turns out our confidence interval goes from 1.186 to 1.254, and we can be 90% confident that the true population mean is in the interval 1.186 to 1.254. Okay, now I've got the calculator up here, and I want to show you how to do x bar minus e and x bar plus e the easiest way possible. So I'm going to go ahead and enter 1.22 minus 1.646 times parentheses 0.65 divided by the square root of 1001. And you'll see when I press enter, I get 1.186. Now, I don't want to have to enter all of this again. So what we can do instead is hit second enter. And what that does is it brings up the last expression that we entered in the calculator, only you can only see the end of it, and the beginning of it has scrolled off to the left. Now I could scroll left one character at a time by hitting the left arrow key, but you can have it instantly go all the way to the left by hitting second left arrow, and that gets us all the way to the left, and then it's just a few clicks to get to that minus sign. So I want to put my cursor over the minus sign, and then I want to change that minus to a plus, and now hit enter again, and there's the upper limit of our confidence interval. So again, second enter recalls the last entry that you made, and second left arrow scrolls you all the way to the left side of the command you're editing. Now let's talk just a little bit about what happens to a confidence interval when you change the confidence level and when you change the sample size. If you leave sample size the same, then increasing the confidence level will make t sub alpha over 2 larger, and that's going to make the interval wider, or in other words, less precise. On the other hand, if you decrease the confidence level, that's going to make t sub alpha over 2 smaller, and the interval will get narrower or more precise. So to help you remember how this relationship works, visualize a dartboard. The larger a target is, the more confident you can be that you'll hit it. So if you have a bigger dartboard, that increases your confidence that you can hit the board. In the same way, as long as we're not changing n, you can be more confident of trapping mu in a wider interval than you can be of trapping mu in a narrower interval. So as long as sample size is staying the same, increasing the confidence level makes the interval get wider, decreasing the confidence level makes the interval get narrower. On the other hand, if we keep the confidence level the same and just change n, then increasing the sample size will make the interval narrower, and decreasing the sample size will make the interval wider. That's because n is in the denominator, so making n larger makes the margin of error actually smaller, and that makes our interval narrower. Now here is another confidence interval example, and this one says travelers pay taxes for flying, car rentals, and hotels. The following data represent the total travel tax for a 3-day business trip in 8 randomly selected cities. And part A says, since n is less than 30, use a normal probability plot and a box plot to determine if the t-interval is appropriate for this data. Okay, so I have entered those 8 values into my list 1, and now what we need to do is look at a normal probability plot and a box plot. So I'm going to go second y equals, and I'm going to change stat plot 1 to a normal probability plot first. Let's hit enter here. I will arrow down and then right arrow until I get to the normal probability plot. Then I'll press enter. It's going to pull my data from L1. Everything looks good there. So now let's graph and zoom 9. And here is our normal probability plot, and that does look like a pretty straight line to me. So I feel pretty good about saying that the population that this data came from is normally distributed. Okay, now let me go second y equals again, and let me just change that plot type to box plot. And since we are looking for outliers, I'll make sure that I select the type of box plot that shows me outliers. So now I'm going to enter and just go ahead and hit graph. And here is our box plot. We could zoom 9 and make sure that all the data is showing, but that's our box plot and there are no outliers. So since the normal probability plot looked good and there are no outliers in our sample, we can feel good about going ahead with the t-interval method for this sample. Okay, now part B says determine a point estimate for the population mean travel tax. Well, remember that a point estimate is just a sample mean. So with our sample data already entered in the calculator, all we have to do is run the one variable stats command, and you'll see that x bar is 83.349. Now part C says construct and interpret a 95% confidence interval for the mean tax paid for a 3-day business trip. Okay, we know that x bar is 83.349. We know from the one variable stats screen that S is 12.324. Now make sure you get S and not sigma because this is sample data. Therefore, we need to make sure we use the sample standard deviation. We know N is 8. Because N is 8, we know degrees of freedom is 7. Now, confidence level we know is 0.95, and that means that alpha is the complement of that, so alpha is 0.05, and that means alpha over 2 is 0.025. If it helps, you can draw that on a diagram. The area in the middle between the two t-scores that we're looking for is 0.95, and that means the area in the tails is 0.05, and that means the area in each individual tail is 0.025. Now using alpha over 2 of 0.025 and degrees of freedom 7, you can go to the t-table and find that t sub 0.025 is 2.365. Now we can find E. E is t sub alpha over 2 times S over square root of N. Now be careful here because some people will accidentally put degrees of freedom here. We only use degrees of freedom when we're at the table. So we always use N here in the formula. And so it's T sub alpha over 2 times S over square root of N. And we'll just put that straight into the calculator. So the lower bound of our confidence interval is going to be X bar minus E, which is going to be approximately 73.044. And the upper bound of our confidence interval is going to be X bar plus E, so that's going to be approximately 93.654. And I hope you'll take advantage of the little calculator trick I showed you before so that you're not spending too much time entering these numbers into the calculator twice. Now that we have calculated our confidence interval, don't forget we also need to interpret the confidence interval. So we had a confidence level here of 95%, and that means we can interpret this by saying we are 95% confident that the true population mean is in the interval between 73.044 and 93.654. Now in Part D, they ask, what would you suggest to a researcher who wants to increase the precision, that is, narrow the interval, but does not have access to additional data? Now, if he doesn't have access to additional data, that means he can't change the sample size. Let's think about our confidence interval formula, and I've replaced E with the formula for E here so that we can see what's going on. Now remember, he can't change N. If you want to affect the width of a confidence interval and you can't change N, the only other thing you have control over is the confidence level. Now remember what we talked about a few slides back. You can be more confident of hitting a bigger target. So a wider confidence interval is going to be associated with a larger confidence level. If you need to narrow the interval, you need to decrease this area here, which means you need to decrease the confidence. So I would say if we can't increase N, the only way to make the interval smaller is to decrease the confidence level. Now the calculator does actually have a t-interval function, and sometimes if you just need a quick confidence interval, you can use that. Please do not use this on any show your work problems because it does all the work for you. But I do want you to know how to use it, and maybe you can use it to check your work now and then, or you can use it for a quick multiple choice problem on an exam. So let's look at the first example we did together, and we'll have the calculator find this confidence interval for us. Remember, this first one we did together had a sample of 1,001 Americans, and it said the sample mean of the time spent eating or drinking each day for those 1,001 Americans was 1.22, and the standard deviation of the sample was 0.65, and they asked for a 90% confidence interval. So to get to the confidence interval function, you're going to hit Stat, and the function we want is under this Tests submenu. So use your right arrow key to arrow over to the Tests submenu. And the one we want is actually number 8. So you could either scroll down or you could just hit 8. And I'm going to scroll this time so you can at least see the name of it. We want the t-interval. Remember, we were calculating confidence intervals using the t-distribution. So that was a t-interval. And now I'm just going to press enter. And this is the same screen whether you have the new operating system or the old operating system. The calculator is going to give you a choice between using data and statistics. If you choose data, it will pull from whatever you have stored in list 1 for X bar and S. But if you choose statistics, it will let you enter your own X bar and S. And of course here we do not have the raw data, so I'm going to use the right arrow key to arrow over to Stats, and then I'm going to press enter. So you can see now that Stats is selected, and notice that it's offering me an X bar and an S. It's just getting that from what I have in list 1. But that's okay, we can just enter our own statistics. And the statistics given in the problem were X bar equals 1.22, and then arrow down, and S equals 0.65, and then arrow down again. We had 1,001 Americans in the sample, so 1,001, and arrow down again. This problem asked for a 90% confidence level, so we need to enter 0.90. I'll just put 0.9, and then arrow down one more time and hit enter for calculate. And there is our confidence interval, and you can check this against the numbers that we found when we did the work ourselves. Our confidence interval goes from 1.186 to 1.254. And here it's showing you the X bar and the S and the N that were used to calculate this interval. And this is just for verification purposes because we entered these numbers ourselves. Now I also want to do the second example with you because on the second confidence interval example we did, we had the raw data. So I want to go through that with you on the calculator. I already have these 8 values entered in list 1. And so now I'm going to hit Stat, and I'm going to arrow over to the Tests submenu. And again, I'm going to use option number 8 because that's T interval. And this time, since I have the raw data and I don't have X bar and S given in the problem, I have to use the raw data to find those numbers. I will arrow over to Data and choose that. So now I'm going to press Enter, and it asks us to verify that our data is in list 1. And if you had frequency stored in list 2, you could enter that here, but we do not. All of our data is in list 1, and we just want each number counted one time, so I'm going to leave frequency 1. Now arrow down again. We can set the confidence level, and on this particular example, the confidence level given in the problem was 0.95. So I'll just enter that, and then arrow down and press Enter to calculate. And this confidence interval goes from 73.046 to 93.652. And you might notice that these numbers are slightly different from the ones that we got when we used the formula to construct this confidence interval. So what's causing the difference? Well, one thing that's causing the difference is, remember, we used a rounded off value for X bar and S, and the calculator keeps several more decimal places than we did. So that's one thing contributing to the difference. And the other thing is that our t-table gives us t-scores rounded to 3 decimal places, but the calculator does not use those rounded off values for t. The calculator's t-scores have lots more decimal places. So we can find small differences in the calculations, and what we're seeing here is a difference of 2 thousandths in each of the numbers. So this one is 2 thousandths larger than we calculated using the formula, and this one is 2 thousandths smaller than we calculated using the formula. Not a big deal, but it is just something to be aware of. Now, I did show you this calculator function for your convenience, but again, please do remember that on show work problems, you'll be required to use the formula, and you won't be able to say that you just used the calculator function. So when you're doing your homework, please do the homework by formula so that when you see the show work problems on the quiz, you'll be handy enough with the formula to do it correctly and get full credit. Now we just have one more objective left in this section, and we want to determine the sample size needed to estimate a population mean within a specified margin of error. So imagine that you're in a situation where you know how wide your confidence interval ought to be, and that means that you know how big of a margin of error you can tolerate. Well, this was our formula for margin of error, and you might think, well, if I know E and I know all these other numbers and I'm trying to figure out N, we could just use a little algebra to isolate N here. And that is true, but remember that in order to look up T sub alpha over 2, we kind of have to know N because we have to know the degrees of freedom. So if you're thinking that we need to use algebra to isolate N here, you're on the right track, but we need to use the closely related formula Z sub alpha over 2 times S over square root of N, because we can get a Z score without knowing N. So let's just take this formula and let's run through the algebra that it would take to isolate N. Now, this is one of those algebra things where I'm going to do it with you, and then you'll have the finished formula available on your formula sheet. So don't get freaked out or sidetracked by the algebra here. Just follow through with me. First, we're going to multiply both sides by square root of n, and that's going to cancel the square roots of n here, and that will give us e times the square root of n equals z sub alpha over 2 times s. Now remember, I'm trying to isolate n. So now I'm going to divide both sides by e, and that gives us square root of n equals z times s over e. And now to remove the radical, I'm going to square both sides, and that gives us n equals z sub alpha over 2 times s over e, all squared. Now the thing is, you're very likely to get a decimal number here, but of course n needs to be an integer. Usually when we round from a decimal to an integer, we round to the nearest integer, and if the decimal value is below 0.5, we round down, and if the decimal value is 0.5 or more, we round up. Here, that would not be a good idea, because if we ever round down, that's going to cause e to be bigger than we want it to be. So what we need to do is just always round up. In order to keep e from being larger than specified, always round up to the next whole number. Don't round off to the nearest whole number. So even if this came out 18.02 or something like that, I would still round up to 19. Now let's look at a couple of examples together. This says a researcher wanted to determine the mean number of hours per week that the typical person watches television. Available data suggests that S equals 7.5 hours. So part A, how many people are needed to estimate the number of hours people watch television per week within 2 hours with 95% confidence? Well, let's start by looking at the formula for n. We know n is equal to z sub alpha over 2 times s over e, all squared. So let's start with what we know. They told us in the problem that S equals 7.5 hours. They also told us that we're trying to estimate the number of hours people watch TV per week within 2 hours. So 2 is our margin of error. And now we need to figure out z sub alpha over 2. Since we're using a level of confidence of 0.95, that means alpha is 0.05. That means alpha over 2 is 0.025. So what we need is the z-score that has an area of 0.025 to its right. So you can go to the z-table and find this, or just a little hint, you also can go to the bottom row of the t-table and find this. In the column for 0.025, on the very last row, you'll find the z-score that matches an area of 0.025 in the right tail, and that z-score is 1.96. And so now we have all of the pieces. Now we can say n equals 1.96 times 7.5 divided by 2, all squared. Put that in your calculator and do not forget to square it. A lot of people forget to square it. And you'll get 54 point something, and of course that needs to round up to 55. We always round up to the next number. And let's try again with part B. How many people are needed to estimate the number of hours people watch television per week within 2 hours for 90% confidence? Okay, so again, we still have the formula over here. We still have E equals 2. This time alpha is 1 minus 0.9, so alpha is 0.1. That means alpha over 2 is 0.05, and that means we're looking for an area in the right tail of 0.05. So again, even though it's a z-score, go to your t-table and look at the bottom row. In the 0.05 column on the bottom row, you can see that z sub 0.05 is 1.645. And now we can plug into our formula. N equals z sub alpha over 2 times s all over e, total squared. And that comes to 38 point something, which we will round to 39. So for a 90% confidence level, we would need 39 people in our sample. For a 95% confidence level, we would need 55 people in our sample. And that's really all there is to estimating sample size for a specified margin of error.